Imagine you have a complex molecule, perhaps a life-saving drug or a fragrant perfume, and right in the middle of it sits a stubborn oxygen atom, double bonded to a carbon. This is a carbonyl group. Now, what if you wanted that oxygen to simply vanish? Not be swapped for something else, but completely erased, leaving only a simple carbon chain behind. In the world of organic chemistry, stripping away an oxygen atom like this is surprisingly difficult. But there is a classic, elegant solution that has been a staple in laboratories for over a century, the Wolff-Kishner reduction. Let's look at the overall transformation. On the left, we have our aldehyde or ketone. On the right, after the reaction, that carbonyl group has been converted into a simple methylene group, a carbon bonded to two hydrogens. To make this happen, we need two key players, hydrazine and a very strong base, usually potassium hydroxide, all cooking in a high-boiling solvent like ethylene glycol. But how do we go from a double-bonded oxygen to nothing at all? The secret lies in a clever bait and switch using nitrogen. Let's visualize the first stage. Imagine the hydrazine molecule, two nitrogens, each with their own pair of hydrogens, approaching the carbonyl. The nitrogen attacks the carbon, water is kicked out, and we form what's called a hydrazone. Notice how the C double bond O has become a C double bond N. We've essentially swapped an oxygen atom for a nitrogen-based handle. This is the setup for the real magic. Now, things get aggressive. We introduce the strong base. As you can see here, the hydroxide ion searches for the most acidic spot, which happens to be one of the protons on that nitrogen end cap. When the base plucks that proton away, it leaves behind a negative charge. Watch what happens next as the electrons begin to shuffle. This negative charge wants to resonate, to move closer to the carbon. As it shifts, it forces the carbon to take on a negative charge of its own. This is a carbanion, and it's incredibly hungry for a proton. It quickly grabs one from the solvent. But we aren't finished. There is still one more hydrogen on that nitrogen. The base strikes again, removing it. Now look closely at the nitrogen atoms. They are sitting right next to each other, held by a double bond, with a negative charge ready to collapse. And here is the key insight, the aha moment of the entire mechanism. Nitrogen gas, N2, is one of the most stable molecules in the universe. It is a thermodynamic sink. The molecule wants to become N2 so badly that it provides the driving force for the entire reaction. In a final, violent snap of electrons, the two nitrogen atoms form a triple bond and fly away as bubbles of gas. They leave the carbon atom behind with a final negative charge. One last proton is snatched from the environment, and just like that, the oxygen is gone, replaced by two hydrogens. It's a beautiful bit of molecular engineering. By temporarily swapping an oxygen for a nitrogen handle, we create a pathway where the sheer stability of nitrogen gas pulls the entire reaction forward. Next time you see a hydrocarbon chain that used to be a ketone, remember the Wolff-Kishner. It's a reminder that in chemistry, sometimes the best way to get rid of something unwanted is to turn it into something so stable it simply floats away.